sorry. Okay, rotate. Okay, correct. That is rotate in a circular path. In a circular path like this. And if you shine the light from above, and at the bottom you have a screen, and you look at the shadow of the object. Okay, if you look at the shadow of the object, what will you see if you look at the shadow when the object rotates in a circular path?
Straight line. Straight line.
Yes, the straight line. But can you give more detail on this line? You will not have the straight line. You will have the shadow of the object move in a straight line. Right? And can you give more detail of this motion? If at time equal to 0, okay, if I say that at t equal to 0, the object is here, okay, and at t equal to some time, okay, if I say that at t, the object is here, and it makes the angle, some angle here. The angle, we can calculate the angle if we know the angular velocity. Okay? If we know the angular velocity of the object, we know that the angle here will equal to the omega t. Right? The omega t. And if I look at the shadow of the object at time t here, if the radius of the circle is v, if I say that the radius of the circle is v, what is the distance from the center point here to the position of the shadow at time t? What is the distance? Okay, you can see that you know the angle, right? You know the radius of the rotation. The distance here will be v cos omega t, right? It will be v cos omega t. So it means that if you rotate the object with the constant angular velocity, if you rotate the object with a constant angular velocity, the shadow will vibrate or will oscillate as a, can you remember this? SHM, simple harmonic motion. So it means that the shadow of the object will oscillate back and forth as a simple harmonic motion, and the equation of motion is v cos omega t. Okay, v cos omega t. So you can see that the motion of the object exhibits the sinusoidal function, right? You have the cos omega t here. So it is a sinusoidal function. The object oscillate back and forth as a sinusoidal function. So we can represent, in this case, we can represent the simple harmonic motion as we call this we call it the uniform circular motion. If you have a uniform circular motion and you look at the shadow of the object, the shadow of the object will move as a simple harmonic motion. So you can represent the simple harmonic motion as a shadow, or we call this in the mathematical term or the physics term as the projection, as a projection of the rotation to the screen. Okay, it is a projection of the uniform circular motion on the screen. Okay, so we can do this to the sinusoidal function also. So it means that we can imagine the rotation in the imaginary space. It's not the real space in the sense that we don't have the object that really rotate, but imagine that we have the imaginary space and have some imaginary object rotate. And when we project it to the screen, we get the sinusoidal signal. And we call that the phasor. Okay. In this figure, just imagine that we have a bar or a rod of something in the imaginary space, and this bar rotates with the constant angular velocity. And if you look at the projection of the tip of this bar to the screen, and you place the screen in the y direction like this is the screen. The projection will exhibit the sinusoidal signal. But in this case, what is the functional form of the shadow? What is the functional form of the shadow? In this case, we project it to the x. The screen is on the x-axis, and we have the cos function. If the screen is on the y-axis, what is the functional form of the shadow? What is the functional form of the shadow if it is on the y-axis? You will have that if we now talk about the signal of the eye, and the length of the bar is I max. So the signal here can be written as I max sin omega t, right? The angle here is omega t. So if you look at the projection on y axis, this become the psi function, right? So you have the psi function. So it means that if you imagine that we have the rotation of what we call phasor, we have the rotation of phasor. We have the rotation of the phasor, and